Okay. So, hydrophobic organic materials which are not compatible with cement. So, you may have to use some binding agents, because again the same thing, you have got a hydrophobic material, you got a hydrophilic, you need something to tie the middle. Surfactants also used for dispersing agent for organic waste in aqueous phase, as you saw in that video. It dispersed the little red molecules. The contaminants and surfactants are mixed prior to mixing with the cement. So you mix the contaminant, some surfactant with it, and then you mix the cement, because the contaminant and the hydrophobic end of the surfactant will bind together, and the hydrophilic end will be available for the cement to attach. We'll come back to that in a bit here. Emulsified asphalt. Emulsified asphalt is another. We will spend some time on the cement this thing, but asphalt emulsion. Okay, what is an emulsion? What is an emulsion? Huh? Oil in water. So, but what is the characteristic of an emulsion? Huh? Not separate. It is in stable equilibrium. Milk is an emulsion, by the way, right? So it doesn't separate. I'm not talking about biodegradability of milk. If you leave it there, it's not going to separate in an hour or 2 hours, right? That's an emulsion. It's a stable emulsion. The liquid and liquid, one liquid dispersed in the other in the form of a stable equilibrium is called an emulsion. Okay. If it is a solid dispersed in a liquid, then it is called a sol, S-O-L. Okay. Solid dispersed in liquid and remaining in a stable equilibrium is called a sol. Okay. So, fine droplets of asphalt in water gives a stable emulsion. Okay. Then what you do is you take the hydrophilic waste and semi-liquid waste treated with emulsified asphalt. You take the waste, you add the emulsion, this emulsified asphalt to it, or these fine droplets of asphalt in water. Okay. What does the asphalt do? Goes towards the hydrophobic material. Okay. The mixture will and once it destabilizes and takes the hydrophobic material, the asphalt goes after the hydrophobic material, covers it. Asphalt is very hydrophobic, and then eventually the whole thing settles out as a globule. Are you with me on that? So if you have a mixture, which is you take an emulsified asphalt, which is a stable emulsion. Okay, if you cannot visualize it, think of it like milk, for example. Fine globules of asphalt in water. The asphalt will gravitate towards the hydrophobic material. The whole thing settles out, and the water and the hydrophilic material are on one side. So that's emulsified asphalt. The other is bitumenization. Now, so what is the characteristic of bitumen? Bitumen is the one that they use in roads, right? One of the characteristics of bitumen, it is a binding material, but it is also resistant to almost anything, right? It is a very resistant material. So one thing you can do, if you have your you can take your, think of all these, you can take your waste material, whatever be your waste material, and you can mix it with bitumen. Okay. Bitumen has an extremely low permeability, hot bitumen. Okay. So mix it with hot bitumen, it has a very low permeability, and the whole thing is now encapsulated in this bitumen, right? And bitumen is pretty much resistant to everything, acids, alkalis, anything at all. So it's going to be there forever. Okay. So that's another one, is bitumenization. Okay. So we learned 3 of them by this time. Adsorption, in which case you use a sorbent material. We talked about sorption over the last couple of days. Emulsified asphalt is one, but emulsified asphalt you can use for things like paints and so on, paint waste, because you want the paint, the hydrophobic material of paint to separate out from the water. You can use emulsified asphalt, mix it together. The asphalt and the organic paint will just separate out. The water is separate out, and you can do some minor treatment to the water and discharge it. Okay. Bitumenization is not something that you would do for that, but if you have fairly hazardous material that does not volatilize easily, because you are using hot bitumen. If you use hot bitumen, the heat should not volatilize it. Okay, but it will fix it. Bitumen will fix it in that this thing, and now you can put it in a landfill or store it somewhere without any problem. Okay, because it is hot, if there is water, it's going to evaporate. So the volume that you eventually get with your bitumen will actually be lower than the volume that of the original sludge. Of course, there are some concerns with processing rate, how fast you can process, how long you can process, and so on. Okay. Now, this is a interesting technology. Interesting in the sense it has not been practiced as much, called vitrification. Okay, there used to be a company. I haven't been able to locate it since the time I have known of it. There used to be a company which used to do in situ vitrification. So what vitrification does is this. So let's say this is a site that has got let's say radioactive waste, okay, all buried and covered, but you are not confident that it is or let's say it contains mercury and really hazardous material, right? You can't take it out, because if you take it out, you are actually exposing your workers, exposing people living nearby, and so on. Okay, so you think, okay, I'm going to vitrify it. So basically what you do is you can melt the whole thing. That's vitrification. Vitrify, right? You melt the whole thing and then let it set as one big mass of glass. Okay, are you with me on that? So you can either do the melting, either you apply electrical current. So in this particular, let's say, size of this room, you'll put an electrical graphite rod here, a graphite rod there, and so on. You can put this, and you send in a very strong electrical current. Eventually the glass, the silica and alumina, the sand and the clay, which is basically silica and alumina structures, will start to melt, and once it melts, it becomes a more or less monolithic mass, and whatever is present in this environment then gets completely fixed in. Think of it like a big globule of glass. Okay, so you melt the whole thing and you fix it. Okay, so that's the idea of vitrification. It is not cheap, and not everybody does it. There are very few consultants that rather contractors which do it. But it is something to consider in a place where you have either you don't know the contaminants and there is a suspicion that some of them are fairly dangerous, right? Or and then you want to keep it on site or in location. Okay, it will take a while to cool that. So let's say you put it, even if you vitrify today, it might be 6 months before it can completely cool off, and you take the sample out. Okay, so this is that's vitrification. You need to know about it. I don't know whether you can use it. unless you have a special contractor who does these kind of things, but it's still something you should know peripherally. Modified sulfur cement process, the way to utilize waste sulfur. Okay, how do you utilize waste sulfur? Well, you add dicyclopentadiene, DCPD, or cyclopentadiene, 5% of it, react with sulfur to form long chain polymers, which is a thermoplastic material, mix with waste material and cool it. So if you have waste sulfur somewhere nearby, then you can use this one. The advantage of sulfur concrete is it gives more strength than Portland cement concrete, quick setting and resistant to attack by acids and alkalis, acids and salts. There might be, because sulfur dioxide and hydrogen sulfide, which are fairly toxic gases, there might be a concerns around that. So basically what you do is you take the stuff, mix it with sulfur, with sulfur with 5% CPD or DCPD, and then let it set. Okay. The other one that I want that you should be aware of on the stabilization is polyethylene. Now, one of the you guys have taken a course in landfills, right? You know what landfills are? Solid waste deposited there. What? You going to explain what a landfill is? So what's a landfill? It's not a dump. A dump is a dump. A landfill is an engineered dump, I should say. Something that has, you can put your waste there, but it has engineering controls. A dump is just open pit, you put something in and let it be. So the dumping, the concept of dumping, which used to happen a while back, has been dropped and completely no longer utilized. But okay, I think I'm digressing here. I'll come back to this landfill story in a bit here. But so we all know what polyethylene is, right? It's polythene, right? It's those polyethylene material. You know, you have the reason I was going after landfill is because they use that in the base of landfill. You know, if this is this black material, you would see this thick, rolled as a base. If you want to put it in the base of a pond or a lake, not pond, but base of a, where you would like to store your hazardous waste or regular waste, you know, it's a very inert material. The high density polyethylene and very high density, low density LDP, HDP, and so on. Okay, these are polythene, very long chain polymeric material that are resistant to almost anything. Okay, they are very low permeability, so they don't leak. They are fairly inert. They don't get attacked by acid or whatever or any other stuff that's present. And because the inertness, they have a value in forming the base of a landfill. Okay, so this particular polyethylene material, okay, can be used to encapsulate waste. You can take your waste material, mix it with hot polyethylene, okay, and eventually you have this mass, very similar to bitumenization in concept, right? You mix it, and then the material which was leaking and all that is all now fixed in this inert material. Conceptually, it is similar to bitumenization if you think about it, right? And then you can store it in wherever you want to put it, you put it, right? It's this mass. Okay, so there's a whole bunch of different things we can do to solidify and stabilize a waste. We can either, if it's just paint based very thin material, we can use asphalt emulsion. If it is a hazardous material, then depending on the level of hazard, we can do bitumenization. We can do polythene mixing with polyethylene, not polythene, polyethylene, and store it. We can use it with modified sulfur. Okay, so if you have sulfur, that is sulfur concrete. So each of them you will require some level of pre-testing to find out how much you want to use. You don't want to use too much more bitumen than what you think you need, right? You don't want to be same thing about polyethylene. If you need X amount, you don't want to be using 5x, 4x or something, right? So that's something you need to do some, and you want to also make sure it is not leaching. How will you make sure something is not leaching? How will you make sure that it doesn't leach? So there is a process, there is a procedure. It's called toxicity characteristic leaching procedure. Okay, TCLP. You have to conduct a TCLP test. It's not that, well, I put it in water and shake it for 2 hours. It's not that. You have to actually conduct a TCLP test, okay, to show that it is not leaching. So for example, if you want to use a polyethylene, right, after you have done that thing, you have to chip out a little bit and do the TCLP test, and then show it to the regulators that under this aggressive condition of TCLP, it is not leaching. It is only under that condition that you can be confident that it is now fully encapsulated. Okay, so while you don't want to overuse this material because it costs money, at the same time you don't want to underutilize the material and have a leaching problem. So you see there is a balance there, right? So that's why you need to make sure you conduct some level of treatability studies around that. Okay. Okay, now to come to the most widely used solidification stabilization technique, this thing, which is cement and cement based materials. By far the most widely used method. Okay. In cement and cement based materials, we have Portland cement, we have fly ash, we have cement, kiln dust, lime and slag. Now, amongst this list of the one that is a manufactured product is Portland cement. Okay, prepared, manufactured, and it is cost money. This business of waste management is an overhead. It is perceived as an overhead by the company. It is perceived as it's not a profit generating for the company, maybe for the contractor. So you will have to be aware of the cost implications of it. Okay. So cement, if you can use fly ash, you should use fly ash. And you don't need strength. They're not building a house. You don't need that tensile strength and the compressive strength and so on. You need some strength. Okay. That if you put it in a landfill, it doesn't get crushed. That becomes, you need some strength, but you don't need that kind of strength. Okay. So use of other waste material like fly ash and cement kiln dust, silicates and so on is widely practiced. So let's talk about cement. How many of you have a background in cement? Do you know what cement is? Half of you are civil engineers, right? No? Okay, so you must have known what cement is. You're not? Right? Now to the important question. Do you remember what cement is? Huh? How is cement formed? How do they make cement? Wet method, dry method. So choose a method and tell me how do you make it. How is cement made? Come on. You take clay and what? And what do you do with all that? How do you get to clinker? Fire it at a very high temperature, right? Right. You fire it at a very high temperature, and then you form these clinkers, and then grind it. So what are the composition? What is the, and then you add gypsum to it, right? To retard the setting. So what is the eventual product of clay? What if you do a chemical analysis, what would you get? Isn't it there? Tricalcium silicate, dicalcium silicate, tricalcium aluminate, tricalcium aluminate. These are the four major components of cement, right? You add water and the tricalcium aluminate and tricalcium silicate and dicalcium silicate forms hydrides. Tricalcium, hydride, calcium hydride, calcium aluminohydride, and so on, right? Now, there are 5 types of cement. Okay. What do they call them here? Do they call them type 1, type 2? No, not grade, but different types. Do you call them type 1, type 2? What do you call them? Or you don't have any name or anything, okay. So type 1, type 2, so this basically, forget about the type part, okay. So normal Portland cement, which is the one that we use in a construction. There is moderate sulfate resistant Portland cement, which has low tricalcium aluminate, because sulfate resistant, right. You have high early strength, which is what you need for dams. Then you have low heat Portland cement, so that's the one you need for dams. And then you have high sulfate resistance, which is even really sulfate environment, you will use the high sulfate resistance. So these are the 5 types of cement. Cement hydration, C3A and C4AF first react to form calcium aluminate hydrate. Sulfates from gypsum react with aluminates to form calcium sulfoaluminate hydrate or ettringite. With time, the ettringite reacts with tricalcium aluminate and water to form a different calcium sulfoaluminate. Eventually it reacts, and with all this chemistry, ultimately what happens is you form calcium silicate hydrate. Thank you. Calcium silicate hydrate, CSH, and calcium hydroxide. The final product of whether it is calcium dicalcium silicate or tricalcium silicate is calcium silicate hydrate and calcium aluminate hydrate and calcium hydroxide. Okay. So hydrated cement contains 25% calcium hydroxide, 50% calcium silicate hydrate. Okay. Now, so if you take cement, it is a very alkaline. If you take the pore water of cement, the alkaline because of the 25% calcium hydroxide. Okay. Now bear this in mind. Keep that in mind. We'll come back to it in a bit here. Okay. So this is prepared by mixing and grinding raw materials such as clay, limestone, and others, and heating them to 2800 degrees Fahrenheit to produce clinkers, and then you add 4 to 7% gypsum, 4 to 7% Portland, gypsum. Okay, I'm going to skip this video here. Okay, so keep that in mind. So that's cement. Okay, we all know what cement does. Now, what is fly ash? What is fly ash? Huh? Where is it produced? Thermal power plant, a byproduct of what? Coal burning, right? Fly ash is produced when you burn coal, and thermal power plants burn coal in large quantities, so you get fly ash there. It is the one that goes to the top. That's why it's called fly ash. The one that goes to the bottom is called bottom ash. Okay, the bottom ash. So coal is coming from coal seams. If there are things in the coal that does not burn, like clay material, that will become a part of the bottom ash. Okay, the thing that goes from the top are basically. So how do you burn coal? You fire it at a very high temperature, right? And you have so it's fine material coming from the top. Okay, if you look at the conditions of forming cement, there is some similarity between the burning of coal. The carbon is gone, but the silica and alumina that are present in the maybe there is some clay and all that will actually be present in the so-called fly ash. It's a very fine material, more like silt. Okay, and so it has pozzolanic properties. What's a pozzolan? What's a pozzolan? A pozzolan is a property when you add water, calcium, lime and water to it, forms cementitious material. Okay, it's a weakly cementitious material, fly ash by itself, because if you look at it, also has some amount of reactive silica and reactive alumina. Cement has a lot more, fly ash has a lot less, but it is there. It might also have some lime by itself, so those are known as self-cementing. Otherwise, you add a little bit of lime, and this reactive silica, reactive alumina will start to have similar reactions and form calcium silicate hydrate and calcium aluminate hydrate. Okay, so the reason I am spending time with fly ash is I know we have a lot of fly ash here as a waste. Okay, you also have a lot of waste here. Maybe the two can go together. Something to think about. Okay, because if you have waste product, that if solidification is a technology that you think would be useful for a particular problem, look at your fly ash. There is a lot of fly ash here. There's a lot of coal thermal power plants. Maybe add a little bit of cement to it, modify your fly ash, and maybe you may have a solution. Okay, so fly ashes that are derived from anthracite and bituminous coal exhibit pozzolanic properties. Fly ashes derived from lignitic and subbituminous coals have both pozzolanic and self-cementitious properties. What you see in the bottom there is a figure of fly ash particles. You know, they have these little spherical particles in the form of cenospheres. Okay, I want to draw, so see this calcium hydroxide. These react with calcium hydroxide to form calcium silicate hydrate. Okay, a pozzolan is what? You add lime and water to it, it will form cementitious material. Okay, what do you have in cement as a byproduct? We just talked about it. What do we have in cement as a byproduct? I just said that. Calcium hydroxide, right? This said that it is alkaline. So we have calcium hydroxide in cement. So you add cement to fly ash. the fly ash can utilize the calcium hydroxide that is produced in the hydration of the cement to form hydration material, right? So it will actually be beneficial. You see the symbiosis here, the benefits that one can. So adding some fly ash with cement is beneficial. In fact, many cement is actually uses fly ash. A part of the cement is replaced with fly ash in your actual cement, the house construction. It's not 100% cement, it's cement with some fly ash in most cases. So cement kiln dust is another one. This is the dust from a cement kiln. Contains varying amounts of raw feed, calcine compounds, alkali compounds, chlorides, and so on. This is the dust which is, remember, cement is a manufactured product, and any manufactured product has specifications to meet. When you buy cement, there is an expectation of it meeting its manufacture, right? So there are things which in any manufacturing process which don't meet the criteria, right? They have to be thrown out. This one is the dust from the cement kiln, which is not the cement but has some properties. For our case, we don't need strength. We are not worried about so many MPAs or whatever. We don't want it to be on the floor so if somebody stands it falls. All we want is something that fixes the problem that we have. That we can put it in a landfill, it meets the TCLP criteria, and we are gone. Right? We move on to the next project. It's not that we want a strength, we want whatever, right? So we have a very different motive. So the CKD is another one. Varying properties depending on cement kiln property. Operation CKD contains some lime and can be used instead of lime. Now lime is usually in demand, right? So the CKD will have some reactive silica. This will react with lime and water to form calcium silicate hydrate. Weakly cementitious CKD can be used as a solidifying agent. All right, the next one is slag. Okay, waste product. Blast furnace slag contains ferrous ions and reduced sulfur compounds. It acts as a reducing agent and is used with Portland cement to stabilize heavy metal contamination. Slag can be alkaline or acidic. An alkaline slag reacts in the presence of water. Slag is, as you see in the picture there, you can see that that's a slag. These ones. It's also another byproduct. So we'll come back to the solidification part in a second here. So additives that are used in cement based process, you can use fly ash, you can use silica, you can use clay, you can use zeolites, because if you have a waste that has got soupy kind of material, you want to make sure the water is absorbed and removed, right? So some of these materials absorbing water may also absorb metals and so on. Absorption of water will reduce water and improve water cement ratio, pozzolanic reactions, and so on. You can also add sodium silicate. Now here is the question. So how does cement actually work? So there was a thought that maybe because you fix it in cement, it remains in a low permeable matrix, right? But actually cement binds with the calcium silicate hydrate to form M calcium silicate hydrate. This is a bond, okay? It's not just sitting on the periphery fixed in a low permeable matrix. If it is sitting on the periphery fixed in a low permeable matrix, because once you solidify and you've gone through the solidification, you have to take that stuff, crush it, and put it at a low pH solution and shake it for a period of time to show it does not leach. If it is just fixed in the sense that it is just trapped in a low permeable matrix, Once you crush it, it will go out. The reason you have to do that test is because that cement block is now going to go to a landfill. Okay, and in the landfill, it is a very aggressive environment. It's got a pH of 4, 3, 5, something around that range. You don't want that thing to start leaching out and then become a problem. You want it to be fixed in the sense that even if that thing gets crushed, because in the landfill you got all these trash masters and all this equipment running here and there and stuff on the top, so that block of cement will not remain there. It might get broken out, and once it breaks out, you don't want it to come out. So cement has been shown that it actually gets, these metals are converted to hydroxides, silicates, sulfides, and that low soluble precipitates, and eventually becomes a part of what it is. So here it is. Interaction between metal ions and calcium silicate hydrate leads to the formation of metal calcium silicate hydrate, or by substitution it releases calcium and gives out. What is the individual metals and Portland cement? Okay, the laboratory studies may be required to determine formulation. If you have cadmium, forms hydroxides and silicates, relatively stable, the pH has to be high. Selenium and silver, well stabilized with cement, silver recovered by pretreatment. Chromium converted to chromium 3 and then converted to hydroxides. Stable chromium silicate complexes are formed, and chromium will not be destabilized because of the toxicity things. Copper, nickel and zinc with forms soluble sulfides. Lead, copper, nickel and zinc are amphoteric. Amphoteric means they are soluble at high pH and low pH. The hydroxides form. So you can use cement for all of this. You can see lead and all that, right? So cement is quite widely used for different types of metals and so on. So if you have a metal contaminated site that has metals in it, think cement and cement based material. Maybe that might be your solution. Okay? That is one of the things I would like you to take away from this course, is you should be able to think at the top of your head, looking at the contaminant, what are the technologies I can possibly use. Okay, should I use soil vapor? Okay, asking a few simple questions of the site, you should be able to hone in into a few of the technologies that would work or has a higher chance. Okay, so if you have metals, that's what you should think around. Cement, based. Maybe can I use plastic? Now, what proportion you would use is something you determine from treatability studies and so on. But you should be able to say this might work. Okay. Now, one of the problems with cement is if you have organic compound. Okay. Now, for those of you who are civil engineers and have graduated recently, you remember what do you do if you want to slow the setting of cement? How do you retard it, right? No, not gypsum. Gypsum is okay, but how do you retard a reaction if you want, gypsum is like what? Lead. What about sugar? Did you try sugar? Yeah, and you use sugar, right? Sugar is an organic, it's a retarder, right? If you want to, if you do a lab experiment, want to retard your cement, this thing, you add some sugar, you'll retard it, right? So, because it's an organic. What does an organic do? It interferes with the setting of the cement. Okay. If you add too much sugar, it will stop the reaction. If you add a little bit, it's going to slow it down, right? So, what happens if you have organics in your waste? and sometimes maybe even not work. So think about whether cement will work if you have organic waste. That's bioremediation, right? That's a separate technology. But cement-based technology you cannot use if you have, okay, so here is something. If you have oily waste, there are two kinds of organics. One is the hazardous organics and the other is non-hazardous organics, right? If you have non-hazardous organics, you are not really particularly interested in fixing the non-hazardous material. You might have a little bit more flexibility. If you have a hazardous organic, then you cannot use cement-based material. And roughly with greater than 1% hazardous organic, you should not use. Straight as that. If you have 1% or more hazardous organic, you want to fix it, cement is not the place thing to do, because cement will not set. And even if it does, it might still leach out. For hazardous, okay? For non-hazardous, the leaching is not such a big concern, and you can use. So the reasons with cement is interference due to coatings. Some organics act as retarders. Organics may act as flocculating agents. Sorption agents can remove interfering compounds. Some organics react at high pH and form less harder. Okay, so the bottom line is this: if you have organics, be careful using cement. Okay, if your organic is non-hazardous and leaching is not such a big issue, you can probably still use it to a certain extent, as long as it doesn't stop the setting and retard forever. Okay, but if it is hazardous, think something else. So these are some of the interference mechanisms. Presence of voids, water cement ratio. If you have too much water, the cement will remain a soup and will never actually set. Air entrainment. I mean, you guys, half of you are civil engineers. I think most of you are civil engineers. You recall what air entrainment is. Salt crystallization. Okay, salt is another one. So if your waste contains a lot of salt, and then the salt will crystallize and will lead to cement not setting. Wet and dry cycles, freeze thaw, all that, chemical reactions, sulfate attack. Because remember, your waste is a waste. You want to make sure that the liquid in the waste is not actually interfering with the setting of the cement, right? Adsorption, complexation, all that stuff. Testing of stabilized mixtures, physical test. You need to find out the physically with soil-like material or whatever. Index properties, density, permeability, strength, durability, compaction. And you have to do the leach test, which is the leaching characteristic, toxicity characteristic leaching procedure, and EP tox test, and so on. Okay, where are these? So we learned through a bunch of these ones, right? Went through sorption and surfactant, emulsified asphalt, bituminization, all that, right? Where are they applied? Where would you apply each one of them? So sorption and surfactant based processes are applied for oily waste, industrial sludges, and soil contaminated inorganics, and low level organics, acid mine leachate and tailings. Emulsified asphalt can be waste from metal foundry processes, paint removal, electroplating waste, metals, cyanides, and so on. Petroleum bituminization, low and medium radioactive waste. So compare this one to the previous one. Bituminization, we are talking about low to medium radioactive waste solution. So this is a more, for lack of a better phrase, a harder hitting technology. Okay. Vitrification, radioactive waste and sludges. Soils contaminated with heavy metals and organic. industrial waste, sludges, medical waste, asbestos waste. This is where you can't dig out, or if you dig out, just the very fact that you're digging out may cause a problem. Modified sulfur cement processes developed for particulate waste such as incinerator waste, contaminated soil sludges, metals, mill tailings, and so on. Polyethylene extrusion, nitrate, salt, sludges, ion exchange resin, incinerator ash. So incinerator ash is, so many places they don't have landfills, okay, or if you have a landfill, that's separate, but you have an incinerator where you actually burn the stuff, right, and you're burning everything, right, everything that comes, which is burnable. Okay, you separate out and you don't let the organics go somewhere, you just burn those ones. So the ash that comes out of incinerator ash will contain, they will contain metals, they will contain some things that didn't burn, all that. So it can have a hazardous component. It's not like fly ash. Fly ash has got very low level of, fly ashes may have a little bit of lead, a little bit of this because of the source of coal, but by and large it's not bad. But incinerator ash is, depends on what you incinerate and what came out of it, right? So it can have chromium, whatever you, cadmium, whatever went into the incinerator. So you will need to do something about that ash. It's not like fly ash where they put it in as a backfill material and so on. You have to deal with incinerator ash and heavy metals. Okay, so how far have I come? 115, right? Should we stop here?